Okay, so let's go over statics practice number 3. Let me draw a picture here, and hopefully I can read it. Actually, Miriam, you may have to help me with the angles because I have writing all over mine. I can't even read it. What's that one? 23.8?
Yep.
Okay. And this one is what, 81.8?
Yeah.
Okay. And then we've got a boulder on the end, which has a mass of 12,250 kilograms. Okay, so right away I'm going to take that and I'm going to figure out the force of gravity by multiplying that by 9.81. Because even if I don't know what else I'm going to do everything I know how to do. And then I will figure out the rest later, which is how most physics problems go. Okay, so there's FG. Next, let me think about a free body diagram here. Let's see if maybe I have enough room. Hopefully I do. Let's redraw it. Is that big enough for you to see? Good. All right, so we've got FG here, and I'll call this T1 and this one T2. And hopefully, because of course I didn't label my answer sheet. I don't remember which one I called 1 and 2, so maybe I'm going to end up doing them backwards. You never know. Okay, so what I'm going to do here is make triangles, right? I make a free body diagram, then I look for everything pointing up, everything pointing down, everything pointing left, everything pointing right. And if I have things that are diagonal, that's where you make your triangles. And it's totally up to you if you want to make the triangle here in the middle, but I'm going to make the triangle out here, just because it will be easier for me to mark, easier for me to see. Okay, so that makes this 23.8, and this is 81.2, although it certainly doesn't look like it. All right, T1x, T2x, T2y, T1y. Okay, so bottom line is I don't know enough information to honestly solve a whole lot here. I do need a system of equations, but since it's in equilibrium, that means that left equals right and up equals down. So I can write myself some equations here. T1y plus T2y, which are pointing up, equal FG. Excuse me. T1x equals T2x. These are my statements of equilibrium. And in fact, if I were, you know, at the AP test or on the AP test, I would actually start with forces up equal forces down, and then forces left equal forces right, because you always want to start with an overriding premise before you start plugging things in. All right, so T blah blah blah. Okay, so let's see what I can figure out here. I'm actually going to start down here with these two, because I only have 2 of them. Okay, so this one is my cosine function, so I know that T1x is going to be cosine of 23.8 times T1, and that will equal the cosine of 81.2 times T2. That's going to be really helpful for me later, because I'll be able to substitute this into this. And that way I can get rid of one of the T's, one of the T1s, or either T1 or T2. Now if I look at this side over here, this is of course going to be my sine function, right? So we're going to say the sine of 23.8 times T1, that's what T1y is equal to, plus the sine of 81.2 times T2 is going to equal FG, and I'm not even going to put the number in right now. I'll just let it be. Okay, so here's my point of attack. I'm going to take this side here, and I'm going to rearrange it. Let's maybe say T2 equals, or I could do T1 equals, it really doesn't matter. And then I'm going to substitute this new equation over here and get rid of one of the missing variables. So if I do that and I get T2 by itself, that's going to be the cosine of 23.8 over the cosine of 81.2 times T1. And I could, shoot, let me go grab my calculator. It should be here someplace. I haven't used it all day, so, okay. And I can tell I'm doing it completely opposite of what I did before, so I have to actually recalculate all the numbers. What a pain, but that's all right. All right, so let's divide that by the cosine of 81.2. So what this does is it gives me 5.98 T1 equals T2. All right, numerically, that's what I'm going to get. Whoa, let's move that over. Okay, so now what I can do here is I can put 5.98 T1 in for T2 over here. So, and in fact, I'm gonna simplify this. Instead of saying sine 23.8, let's say 0.404 T1 plus sine of 81.2 is 0.988, and then T2 is 5.98 T1 equals 120,173 newtons, because that was the FG that I had before. What this allows me to do is it allows me to eliminate one of the missing variables. You okay? You good? Okay. I know I said we weren't going to ask questions, but you're sitting right there. I can't help myself. So, all right, so let me add up the decimals, and I get 1.392 T1 equals 120,173. T1 equals 17,803 newtons. And at this point, I can substitute T1 right there and figure out T2. So if I do that, I get my other answer. All right, but you definitely need to use both pieces of equilibrium in order to do that. All right, did you get that one?
Yes.
Okay, I'm gonna move that over and let's do problem number 2. Problem number 2 is a little vague. It should be worded just a little bit better, but I've been a little lazy, I admit it. All right, so we've got a 98 kilogram bag of birdseed, and we're dragging it across the deck. It's gonna be a horizontal pull because I didn't give you an angle, so we can assume it's a horizontal pull. So make it like a tension because we're pulling on it, and we're gonna have friction going back. We've got gravity, and we've got normal force. Okay, so the only information you're given is mu is 0.445, and you're looking for the force to move the thing at a constant speed. What that tells you is that the forces have to be balanced in your left-right plane of motion. All right, or actually this is really how they do it on the AP exam. They say the sum of the forces in the x direction equals 0, so they're equal to each other. That's how you say, oh, balanced forces, instead of that, left equals right thing that I came up with. All right, so friction is going to be coefficient of friction times normal force, so that will be equal to Ft. And so 0.445 is my coefficient of friction. My normal force is going to be 98 kilograms times 9.81 because it's on a flat surface. We don't have any other up-down forces, so those are equal to each other, gravity and normal force. And I get about 428 newtons based on my memory for that question. All right, so there's our second question. Third question, Atwood machine with 2 bodies. This one's 11 kilograms. This one's 8.60 kilograms. Okay, and it says find the coefficient of friction to keep the blocks at rest. So we're looking for that. We're looking for mu, and as we know, mu is the force of friction divided by the normal force. Okay, when you've got a 2-body system, start with the hanging block. That's the easiest of the two. So when I start with the hanging block, free body diagram very quickly will tell me that I have gravity and tension. If it's at rest, sum of the forces in the y direction will equal 0, meaning they're balanced. Their up and down is balanced. So tension will equal 11 kilograms times 9.81 meters per second squared. So that gives me a tension of approximately 108 newtons. I always round things to the whole number. I just do when it comes to forces. It's not the most accurate, but it serves me pretty well. All right, so there's my tension. Now for my object on the incline, I've got gravity trying to go straight down. I've got normal force perpendicular to the surface. I've got tension going up the plane, and I have friction. Now, in truth, I can't naturally put friction going down. I really need to know more before I decide where the friction goes, because friction can go up the plane or down. Just depends on which one is bigger. So let's, since I'm not going to complete my free body diagram, I'm going to break up my gravity into my triangle. So this is mg cosine of theta here. This is mg sine of theta here. And I want to know what that one is. Because when I compare this one to this one, if they're not equal, that's going to help me figure out where the friction goes. So let's do a little math, and then we'll figure out where the friction goes. Okay, so mg sine of theta, so that's 8.60 kilograms, 9.81 meters per second squared. Sine of 43 degrees, which is given to me in the problem. All right, when I do that, I get 57.5 newtons. So this is really the force trying to go down the hill. And my tension force, as I already know from before, is 108 newtons. Since I have a frictionless massless pulley, it's only changing the direction of the force. So I know it's the same as the one from the hanging mass. So if this one's 57.5 and this one's 108, well, obviously friction's got to compensate for this one because it's not big enough. All right, otherwise this thing is going, oh, it's going to go up the hill. So if I subtract 108 newtons minus the 57.5 newtons, I get a difference of 50.5 newtons, which means that my friction is 50.5 newtons. I think I got to slide this up for you. Let's do that. Okay, almost there. So if I need mu to be the force of friction over the normal force, well, I know the force of friction. It's 50.5 newtons. Normal force is equal and opposite to mg cosine theta. It always is, unless you got, you know, your rope at an angle or something weird, but we don't. Okay, so mg cosine theta. So 50.5 newtons, and this is what, 8.6 kilograms, 9.81 meters per second squared, and then the cosine of 43 degrees, and I plug and chug all that out. On the bottom, I get 61.7 newtons, so mu ends up being 0.818 when I do the math.